Hello and welcome everybody. My name is Hannah Mason. I'm a technical editor at CompositesWorld. I want to thank you for joining us today for this webinar titled The Future of Graphene Enhanced Epoxy is Now, brought to you by CompositesWorld, presented by CompositesOne. The webinar will discuss the results of one of the first neutral head-to-head studies of using graphene in a two-part epoxy system. And to discuss this, we have three presenters on here today, as you can see. The first is Terrence Barkin, Executive Director for the Graphene Council. Terrence founded the Graphene Council in 2013 as a global trade and professional community connecting scientists, academics, producers, end users, and commercial professionals that have an interest in research, development, and application of graphene. Terrence has been building trade and professional associations globally for more than 30 years. Joining Terrence, we have Paul Redinger, Technology Director for Thermosets in the Americas at Vibrance Technologies. Paul has served a variety of roles at Vibrance, and examples of his work can be found in many applications, such as tactile plates at walkway intersections, and a variety of other applications. Last but not least, we have Jason Gibson, Chief Applications Engineer at CompositesOne. In this role, Jason manages growth of composite materials for defense and aerospace markets and is engaged in research and developing innovative materials in the composite sector. He has more than 20 years of experience in the composites industry and holds a PhD in mechanical engineering from the University of Central Florida. So this presentation will be followed by a question and answer session at the end. So if you have a question, you can type it in at any time during the webinar in the question field at the right of your screen. And the webinar is being recorded, and when complete, will be made available to you via email from CompositesWorld. So welcome, everybody. Terrence, Jason, Paul, it's all yours.
Great. Thank you, Hannah. Really appreciate the introduction. And thank you to CompositesWorld for hosting this session. It's really exciting to be here, and I think what you'll see is some really important work that we had concluded. So I've got a colleague, Jason, he's going to be driving the slide set today, so we'll go to the next slide. Thank you. For those of you who are maybe not familiar with who the Graphene Council is, we connect about 35,000 materials professionals worldwide who are all working with graphene in one form or another. About a third of those are academic postdocs, and the other 2/3 are all commercial folks like yourselves on this call, who work with materials and are interested in what advanced 2D materials can do. Let's go to the next slide. Graphene is a really exciting material because it can be used in so many different ways. You probably have heard of graphene, and you've probably heard that graphene is the lightest, strongest, most thermally conductive, most electrically conductive material that man has ever isolated. And for all these reasons, graphene can be used in many different ways by imparting improved strength properties, imparting the electrical conductivity, either for anti-static properties or even for electrical signal conduction, UV protection, etc. There's so many different ways it can be used. But one of the most exciting and most promising and most advanced uses is in composite materials, and that would include both thermoset and thermoplastics. Next slide, please. So graphene can be used in all these different applications, and as I said, it can be used in composites. Some of the main other applications include energy storage or batteries, elastomers or rubber products, in coatings with anti-barrier properties, in thermal management, heat transfer properties, and for sensing, where you're using a single atomic layer of carbon as a sensing platform. And I should have started with that to say, what is graphene? It is this single atomic layer of carbon, or up to and including 10 layers, and we'll cover that next. So when we want to talk about graphene and composites, two obvious platforms include automobiles, and the other would be aerospace. So for the automobile, we all know that composites are gaining a proportion of share of components in the automobile, mostly for lightweighting, but for other specialty applications like containers for the battery cells, for thermal management, for structural components, to reduce the number of parts or fasteners that are needed in an automobile. And in each of these areas, these are also opportunities for graphene to help make the composites even better and make them even more competitive traditionally against metallic structures or metallic parts. Next. And as I mentioned, the same would hold true for aerospace, and in particular, lightweighting is really one of the key objectives there, as it is in automotive. And that's where graphene, by making composites stronger, you're able to use less material, or in the case of using fiber reinforced systems, whether it be glass, basalt, or carbon, we have examples where if let's say you had a 5-ply reinforcement for a composite part, and by strengthening the resin system with that fiber reinforced system, you're able to eliminate 1 or even 2 of those 5 plies. You've saved money by eliminating the material, of course. You also reduce the amount of labor, and importantly, from an engineering perspective, you've lightweighted the part. So these are some of the reasons why this material might be used in composites. Next slide, please. Graphene, as I said, is a single atomic layer of carbon, but it can include material that is up to and including 10 layers. That's according to the ISO definition of what is and what is not graphene. Next slide. And besides the layer count on defining graphene, you also have different forms or types of this material, so that in essence, graphene should not be thought of as a single material, but more like a family of material. And within that family, you have things like graphene oxide, which typically has about 35% oxygen by weight. You can also create graphene oxide and then reduce the oxygen out of it so that you're left with about 5% oxygen. And that gives you a reduced graphene oxide. And both of those materials behave in unique and special ways. Graphene itself might be presented as a powder in a solution or a paste. You also have graphene nanoplatelets, which are stacked a little bit higher than few layer graphene. And finally, you have material that you can functionalize, and this would be adding elements or chemical groups either to the surface or the edges of the individual graphene flakes. And you might do that, for example, to make them bond, maybe even to a glass fiber reinforcement as an example, or in a resin system to aid in dispersing. Next slide. So what is the role of the Graphene Council in this presentation and for this particular project? We recognize that the composite sector needs data about whether or not graphene actually works, and if so, how well does it work? And so we developed an independent, blinded, head-to-head comparison of more than 15 types of graphene material in a standardized 2-part epoxy system. And we used a extremely competent lab. We used the University of Maine with their Advanced Composite Center to do the physical testing. And we worked together with Vibrance with their expertise on doing the master batches of the material, which you'll hear more about in just a second. Next slide. And so with that, the Graphene Council overviewed this project, and then working with our partners at CompositesWorld and Vibrance and the University of Maine, we conducted the test itself. And what you'll now see is an outline of how that program was administered and what the results were. So with that, thank you for your time and attention, and I'll check back with you when we get to Q&A.
Thank you, Terrence. My name is Paul Redinger. I'm one of the technical managers at Vibrance Technologies. As of middle part of last year, several companies, Prince, Faro, and ChromaFlow Technologies, merged to form a new company, a bigger company called Vibrance Technologies. And before I get into the project, I'll tell you a little bit about Vibrance Technologies and what our involvement with this project. Go ahead. Next slide. Okay. So our purpose and our vision and our values is, we bring color and we bring performance and we bring this other little term, vibrancy, to life. Our vision is to be an enduring and sustainable world-class specialty chemicals and materials company. And on top of our values is safety. We are also committed to our customers, our people, to sustainability and the environment. And of course, you can't have any of these things without a commitment to excellence, integrity, ethics, and trust. Next slide. So our business segments vary somewhat significantly. On one side, we have the advanced materials group that deals with electronics, advanced materials, advanced minerals for things like metallurgy, chemicals for electronics applications, batteries, that sort of thing. And then we also have another part of our group which deals with color solutions. We deal with pigments, we deal with color dispersions, and we do specialty pigments and additive and chemical dispersions for the thermoset plastics and coatings industries as well. And we also do have a business division that comes from the performance coating segment, and they do things like industrial porcelain enamels and decorative industrial automotive glass coatings and industrial porcelain enamels. So I come specifically from the color solutions side of this business. And next slide. We have been investigating nanotechnology and the science around nanotechnology for an extended period of time. We've been dispersing carbonaceous nanoparticles for OEM applications for 25 or more years. We don't make graphene. We do disperse it, and we do continue to experiment with ways of customizing graphene for specific applications, including but not limited to transportation, electrical, battery, coatings, and many other applications. So this has been an area of significant interest to us in the past year. And it was a logical fit for us to work with the Graphene Council and with CompositesOne and the University of Maine to promote this whole science for us. Next slide. So in the early onset of this project, we received 19 encoded samples. We didn't know what they were. One thing I can tell you about the graphene samples we received, they were unidentified. They had the code numbers on them describing the differences between or identifying different materials, and they differed widely. There were some samples that seemed to have surface area to our inspection of maybe a neighborhood of 100 square meters per gram. There were other samples that appeared to have surface areas much higher, possibly even above 1,500 per square meters per gram. So what we did was we took these different unidentified encoded samples and we processed them into stable, rheologically consistent, processable liquid master batches that we thought that University of Maine would be able to handle. So in the process of doing that, we took a lot of care to make sure that we not knowing what these particles were exactly, we tried to process them all under the same conditions, understanding, of course, that they were different materials and had to be handled a little bit differently. So we went under a lot of work to make sure that two-dimensional particles were deflocculated and deagglomerated, but otherwise undamaged and undisturbed by our dispersion process. And we also made specific loadings that would vary according to the surface area the graphene platelet has received in order to make sure that we had a stable dispersion, that first of all, and secondly, one that the University of Maine would be able to handle. And once we had processed these samples to rather stringent specifications, we shipped them to the University of Maine where they performed further testing. Next slide. So at the University of Maine, the samples were let down to two specific loadings, to 0.5 and 0.1% in epoxy resin. They were mixed using a high-speed orbital and degassed under vacuum, and a curative package was introduced. And we used a common amine ratio for all samples. So we didn't adjust for any stoichiometry that might have existed on the graphene or any functionalization that occurs. We treated all the graphenes exactly the same. The samples were then mixed, poured into molds at 60 degrees Celsius, cured for 1 hour. They were subjected to a 3-hour post-cure at 160 C, and then they were cut for the specimens were cut for molded panels, subjected to flexural, instron, and notched diazode testing. In general, we saw the performance varied, but we did see some gains, as much as 35% gain in flexural strength, up to 75% gain in flex modulus, and some of the samples exhibited little or no damage to notched diazode values from resulting embrittlement of increasing the rigidity and modulus of the material. And so I will turn the presentation over to Jason Gibson, who will go over the results of the evaluation at the University of Maine. Jason?
Thanks, Paul. So as I mentioned, my name is Jason Gibson. I'm the Chief Applications Engineer at CompositesOne. I've worked in the industry for over 20 years, with 16 of those being with CompositesOne. Now I have the task of presenting the final results of our testing, but before that, I'd just like to take one slide and introduce CompositesOne to you. So we're the largest composite-focused material management company in North America. On any given day, we're supporting our customers' needs by handling over 40,000 unique products from over 600 suppliers. But the key to remember about Composites One is that because we're not limited in our product offerings, we can explore the unique breadth and depth of composite materials we handle to bring you a comprehensive, integrated solution for your specific needs. And we do this by not only delivering the products quickly, but also supporting your team through hands-on technical support across North America. Now, this slide gives a good overview of the geography of our network, and you'll notice that we cover North America through stocking locally with 44 locations. Now, this means that wherever you're located, we could support you by not only stocking the material you need, but by helping you with technical support in your shop with one of our many local technical sales representatives. So let's jump into those results. So as Paul mentioned, earlier we had 17 sample materials shipped to the University of Maine for testing. These samples were anonymized and no one, including myself, knew whose material we were testing, giving an unbiased, objective testing protocol. We took the 17 master batch samples and blended them down to 0.1% and 0.5% loading of graphene by weight into the bis-F epoxy. We then poured the samples into a mold and cured at 140 degrees Fahrenheit for 30 minutes, and then followed that up by a 3-hour post-cure at 320 degrees Fahrenheit. Samples were then cut from the molded panels and tested for both flexural properties and impact toughness. Now, in some of the samples, we saw great improvements in both flexural modulus and strength. But typically, when you improve the modulus of resins, you have a negative impact on the toughness of the system due to embrittlement. And this was true for some of the samples. However, there were some that showed negligible impact to the toughness of the resin while providing excellent flexural modulus and strength improvements. So let's just dive into the details of the results. All right, so first, let me just take a moment and explain what we're looking at on this slide. First off, along the side there, you'll see the sample numbers starting with the control sample. That control sample does not have any graphene enhancement. The first few columns show the results for flexural modulus for both loadings of 0.1% and 0.5%. The next few columns show the flexural strength results, and the final few columns there detail the recorded strains. Now, throughout, we've highlighted the results with colors for quick interpretation. So if you look at that 0.1% loading for flexural modulus, you'll notice significant improvements highlighted in green for samples 9 and 15 through 18, with results as high as 72%. Now, if you look at those same samples for flexural strength, you'll see that all 5 of those samples improved the strength as well. Now, if you move a little bit over more to the right and you look at the detail at the 0.5% loading, you also notice many more samples that improved flexural modulus. However, the improvements were not as high as the 0.1% loading. So with that in mind, it's probably good to introduce the concept of statistical significance on the next slide. So I'm showing 4 different graphs on this slide. All 4 are for the 0.1% loading. These are the flexural modulus, the stress, and the strain, and that bottom right graph are the impact results. You'll notice each graph has a bunch of colored circles on the right. These tell us which results are statistically significant, which simply means that the differences in the samples tested and the control are significant enough that we can be confident that there's a difference. So if the circle is shown in red, it simply means that those results are not statistically different from our baseline, and so we consider the difference negligible. But if the circle is in gray, it means that the samples tested had enough of a difference from the baseline that we can be confident that there is a significant change in results, either positive or negative. So if we look at the flexural modulus results in that top left graph, you'll quickly notice the 5 samples I mentioned earlier have a significant improvement over the baseline. And their circles are in gray, reinforcing that they're statistically significant, which is great news. So let's take a look at the impact results in the bottom right corner for those same 5 samples and see if they affect the toughness of the resin. You'll see that samples 15, 16, and 17 are all in gray. That means that they significantly reduce the toughness of the base resin. That's not good. But both samples 9 and 18 are shown in red, meaning that their impact on the toughness is statistically negligible, which is good news. It means that out of the 17 samples tested, we have 2 that significantly improve the flexural modulus and strength with negligible impact on the toughness of the system. So let's just take a moment and look at the same type of data for the 0.5% loading. So these are the same 4 graphs for our 0.5% loaded samples. Immediately in that top left graph of flexural modulus, you'll notice none of the samples tested showed any statistically meaningful change from the baseline, and all are in red. You'll notice that the spread of results is larger than those 0.1% loading that we showed you on the previous slide. There's simply too much variation in results to have any confidence in them being different from the baseline. Now let's also look at the toughness results in the bottom right graph. Here you'll see that all the samples showed significant change in the toughness, but in the wrong direction. All of them lower the toughness of the base resin. So in summary, none of these results from 0.5% loading are promising. So if we look at just the toughness results for both loading levels, you can see again that the 0.5% loading shows a lot of red and orange in the percent change, and none of that is good. But in the 0.1% loading, you'll see a number of green results that are good, with samples 9 being one of them, and sample 18 being yellow at an 8% change. But that 8% change is not statistically significant for us to know that it definitively has an impact. Now, we also want to do a little bit of an analysis. So let's take a look at some of that. So one thing to keep in mind is that all samples had some form of agglomerations of graphene in them. These agglomerations are where the graphene did not get fully dispersed into the resin. While all samples had some form of agglomerations, each sample had varying levels of this. Now, theoretically, the better dispersed the graphene is in the matrix, the better its performance. So I'm showing a couple examples of these agglomerations under a microscope. Both are at a 2000x magnification. But even at this 2000x magnification, what you see in these images are millions of graphene platelets clumped together. And there are millions more fully dispersed in the resin, but you simply can't see them at this scale. The sample on the left there is from our sample 18 at 0.1% loading, and the sample on the right is from our sample 10 at 0.1% loading. Both of these samples performed well in our testing, but sample 18 on the left performed better than the sample 10 on the right. Now you can see that visually these agglomerations look different. This speaks to the possibilities of the difference in the type of graphene, the functionalization, the morphology, and other physical characteristics. However, this does not lead us to any definitive conclusion other than the simple fact that these samples were all different. Now, we also want to try to understand why the 0.5% loading did not perform as well as the 0.1% loading. So to do this, we looked at sample 18 at both loading levels under a microscope. So on this slide, I'm showing the 0.1% loaded sample on the top left and the 0.5% loaded sample on the bottom left there. By polarizing the image, the graphene is highlighted, and we can calculate the size of graphene agglomerations in both samples. Now, these agglomerations are where the graphene clumped together, and you did not fully disperse into the solution. You can see these clumps or agglomerations on the two images on the left. I've highlighted them in red. You'll notice that not only were there more groups of agglomerations, but the average size of each was higher for that 0.5% loading on the bottom there. And I graphed both the average size and the total area on the right for quick reference. You'll notice a significant difference in both values for each loading level. Now, this information is not conclusive as to why the 0.5% loading did not perform as well, but it does lead us to want to analyze the failure mode via SEM to see if the failure modes of the samples correlates and originates from the agglomerations or just the particles themselves, but nonetheless, we need to dig deeper to understand why it didn't happen. So in quick summary, we have 5 samples at 0.1% loading that showed significant improvement in flexural modulus and strength. Out of those 5 samples, 2 had negligible impact on the toughness of the resin. Now, I want to reinforce that this was a blind study, so there was no bias given to any graphene supplier. However, that also means that we could not optimize for any type of functionalization the suppliers may have done. And as we mentioned, in general, the 0.1% loading provided the better results. Now, moving forward, our plan is to offer additional testing of other graphene samples. This will be done at the cost of the supplier, and will be done at the 0.1% loading for comparison to the original data. And this will be done through the Graphene Council. Now, we also have plans to publish in peer-reviewed periodicals in the future. And we also want to look at other loading percentages to determine what is optimal. We know now that the 0.1% loading is better than the 0.5% loading, but is 0.1% optimal? And then finally, we'd like to conduct testing in finished laminates. We predict improvements in any resin-driven physical properties, like interlaminar shear testing, but we need to confirm in testing of fiber-reinforced laminates. So we've presented a lot of information today, and I'd just like to simplify why this is important. We now know that we can offer a graphene-enhanced resin that produces a stronger, better material. With that increase in strength and modulus, you now have a system that may allow you to produce lighter parts and give the possibility of reducing your ply stack for a given design. Now, we get a lot of questions about cost, and I can confidently say that due to the extremely low loading of 0.1% or 0.001, the cost of the graphene in the finished system is very affordable and is significantly less per pound than the standard bis-A epoxies at our current market prices. And then another selling point is that these are drop-in solutions. There will be no change to your current process. You simply blend in the enhanced master batch into your base epoxy systems with standard mixers. It's simple and easy. Now, before we open up for questions, just a quick reminder of why you want to work with us. At the Graphene Council, you have an independent and neutral source of expertise on the supply chain. They're an incredible wealth of knowledge whose only goal is to promote graphene. At Vibrance, you have a very experienced team of experts with a deep skill set in tuning and compounding nanomaterials. And then finally, at CompositesWorld, you can rely on us to partner with you every step of the way with a market-ready solution that we can stock locally for you while offering technical support in your local shop as you implement it in your process. So with that, we'd like to go ahead and open up for questions. Hopefully Hannah has some set up for us to answer. Hannah?
All right, thank you so much to all of our presenters. That was great to hear. So like you said, we have several minutes now for questions for our presenter. So attendees, if you have a question, now's the time. Please use the Q&A field specifically on the right of your screen. We're going to start with this one. Does CompositesWorld have a commercially available product we can buy today?
Yeah, that's a simple question with a little bit more complex answer. We do have it, but we are being careful on how we roll it out. So we're going to work with a few of our key customers to make sure we support them throughout the beginning of the process, make sure it implements properly, that performs as well as we expect it to. And then we plan on rolling it to others as we have success with those first few we trial it with. So what I'd suggest is that if you are interested in this, reach out to your local Comp1 salesperson. Let them know what you're trying to accomplish. Let them know the application, how you want to process it, the kind of volume you're looking at. And then we can collect all that and decide how we roll out as we move on beyond our first few key customers.
Okay. And what applications do you think will be the most improved by this product?
Well, any of us can answer this, but I'll start. I believe that we'll see good results in any resin-driven property. So that means if you have a part that is defined by, say, interlaminar shear strength, anything that your resin is your inhibiting factor, we believe that you're going to be able to enhance this with our system. I will say any fiber-driven properties, you probably won't see as much of an improvement, something like tensile modulus and strength, that type of thing. But for practical applications, we're targeting pressure vessels, any kind of prepreg application where stiffness is important, flexural modulus, that type of thing. So that's kind of where we're envisioning it, but we're open to ideas if the customers have applications they think that it would really do well. Anyone else want to answer that?
Well, I think you covered it. I was going to say, with the hydrogen storage tanks, with the pressure vessels, I think that's a really interesting area where we've seen that the graphene helps mitigate microcracking and add strength, so you can get a little bit thinner high pressure pipes, right? So extruded, you can also have the extruded product. So I think you covered it pretty well.
All right, that's awesome. So we have a question here talking about, so this study focused on flexural properties and asked, have you tested for, water resistance, chemical resistance, durability, fatigue, or other types of properties at this point? Or I guess, are there plans to do so?
We haven't at this point.
I think the answer to that question is that those are application-specific characteristics and properties, and those are things that we would support people doing that type of testing and provide people samples to do the work. But those are things that are kind of application-specific, and the companies that are planning to work investigating graphene for their application would kind of need to do that type of work as relates to their own work.
Okay. What are the characteristics of the graphene that enhance the properties of the resin? Is that something you're able to expand on a little bit more?
Well, we tested, if I could just speak to this briefly. So we tested 15 different types of graphene in the original test, and that included a graphene oxide, a reduced graphene oxide, a functionalized material, graphene nanoplatelets, few layers, so something like 3 to 5 layer, as well as 7 to 10. We've not disclosed the names of the companies and the actual materials, but in general, we're looking at a material that's less than 10 layers. Graphene nanoplatelet was the type of material, and another one that performed well was a functionalized graphene material. But let me kind of preempt some of the questions or address some of this in general, because there's other questions about, applications, about flammability, about barrier protection, about chemical resistance, etc. This particular study, we wanted to be able to do a head-to-head comparison because this kind of study had never been done before. You have a lot of data about individual performance of graphene in different applications. So, for example, everybody may be familiar with the fact that Ford Motor Company used a graphene-enhanced polyurethane material in the engine compartment for the F-150 and for the Mustang. And they did that for thermal heat transfer properties. But they also got a reduction or a dampening effect in vibration. It also reduced the flammability, and we've seen this with other applications of polyurethane with graphene added to it for strength and wear resistance, that it reduced the flammability of the material. This is not unusual for us to see when graphene is added for a primary purpose, and in this case, we were looking at strength properties, that it has additional beneficial properties. We actually have yet to see where graphene has been added for a primary property and it had a significant negative impact. And in this case, what Jason presented, you would expect to have embrittlement, right, by adding strength. And we had a case here where graphene added strength without significantly negatively impacting embrittlement, which is quite unusual for a material because usually you have trade-offs. So I'm going to stop there, but I think that we've got some really great questions. This study answered some of them, but there's additional data that might answer some of these other questions as well that's out there.
Right. Okay. Looking through the question list here, like you said, there's quite a few here.
Can I make one comment about graphene while you're doing that?
Yeah.
It deals with the reason for mechanical property gains. Graphene is as a tensile strength that's 18 times stronger than steel. What you have to do to gain properties or gain properties from it, it's inherent to the material. But what you have to do to get properties from the graphene is you have to have something called load transfer, wherein a polymer transfers a portion of its load to the inherent strength of the graphene to reinforce it. And as long as there's a sufficient bond between the resin and the graphene to allow for that, then you can have gains in properties. That's all I wanted to say.
No, yeah, that's a very good point. Thank you for making that. I guess we'll go next question here. What difference could one expect in processing using graphene within the resin system, specifically storage, mixing, impregnation, etc.?
So I guess I handle that because I'm a rheologist. And one of the things we tried to do is we tried to make sure that all the samples that we sent off to University of Maine for the testing were rheologically consistent and handleable. So a lot of it really depends upon your process and what you're doing, but it's easy to mix into a resin system, and it's easy, in its dispersed form. Go ahead.
Oh,
and if it's in its dispersed form, it's easy to get incorporated into resin, and it's easy to get to where you can use it and make use of it, especially at the dilution loadings of 0.1% total loading, generally speaking.
Yeah, so I'll jump in there and just add to what he's saying in that at that 0.1% loading, it doesn't have a big impact on the resin itself once it's let down in. It's a very easy dispersion. You use standard shear mixers. The hard part is getting at that 20% loading into the bis-F slurry, which is what Vibrance did for us. And then once it was in there, it stays in there. It's still in the mixture. It's not falling out of it to this day. So once you use a standard mixer, which everybody that's using an epoxy, a two-part epoxy, has to blend in their hardener anyways. So the envision is that you let this in, the slurry in, to let it down to that 0.1% with your standard mixer. Then you add in your hardener and blend that in, and then you're ready to go. It's no change to how you process anything. It's just an extra mixture you're throwing in there.
Okay. There's a couple of questions here on resin systems. I know this was a two-part epoxy, obviously, as the focus of the study. Has this application been studied in other types of resin systems? Or are you able to speak to that in any way? I've seen vinyl ester mentioned, a couple of other ones, urethane. Is that something you guys have looked at this point?
Not in this particular study, but there is data, and that's kind of what we do with the Graphene Council is we inventory both research reports and commercial applications. Basically, any of the resin systems or chemistries, graphene has been compatible. We should think, again, graphene is 100% carbon. And it has a lot more to do with, which system it goes into, the rheology of it, and how you're doing the dispersing. Has to do with the individual particular particle size. We have to remember that a single atomic layer of graphene is 1/3 of 1 nanometer in vertical height, or z-axis, and it could be submicron to several micron across in lateral size. Because I think there was a question here about surface area and rheology, and that does have a big impact. And I'm sure, I can't remember if it was just mentioned, but when the master batches were being formulated, some of them could be compounded to as much as a 20% weight of the graphene, and some were, the max you could get was about 2 or 3% because of viscosity issues. So there's a big range in how individual particles of graphene work. And so, one of the things I would say here, the reason why this worked so well in this particular grouping in this team was the expertise between the Graphene Council, which organized the graphene producers, right? We got our producers to work together in this. And then you have experts like CompositesWorld and Vibrance on the compounding and the chemistry side of this to get the formulation right. There was a question if the graphene was provided in liquid form or powder. This was all powder, right? Ideally, for you if you're a consumer of this material or a composites maker, you don't actually want to handle the graphene yourself. What is proposed here is the ideal solution of having the graphene already master batched into a resin system that you can just use, and as Jason just said, without having to worry about the compounding part of it yourself, and just go ahead and use it and get the benefit of the properties without having to handle graphene as a nano powder. And when we talk to anybody, and for all applications, we recommend this approach of working with master batches, work with a graphene producer or a specialty company who can do the compounding, so that you're not having to deal with the nano powder if you can avoid it.
Okay. When I go, there are a couple questions in a row here that are kind of go back to properties of graphene and benefits that graphene can have in general, which I know you listed several of them at the beginning here. Specifically, a couple questions here. Can graphene improve flammability? Can you speak to electrical property enhancement and thermal performance?
Well, we've done some research on graphene as it relates to thermal, thermal analysis and thermal performance of materials. Yes, it can increase your thermal conductivity at certain loadings. The threshold's a little higher than what you achieve for mechanical properties. You can achieve a degree of, say, static dissipative conductivity using graphene. Again, the threshold varies a little bit for what you would use if you're trying to achieve mechanical properties. What I think is really interesting, though, is when we've done TGA studies, we've seen anywhere from 5 to 10, sometimes even higher increases in the temperature of onset of degradation. In other words, the graphene seems to behave as actually a protecting material and a stabilizer in some cases for the epoxy resin and or urethane or other materials that we've tested it in.
Okay. In the study, how did you measure the agglomeration?
So I'll answer that. what we were doing there was under a microscope, we were polarizing the image. This particular digital microscope had the capability to polarize and then take that digital image and calculate that area. It's not 100% accurate. It's not perfect, but it's the only way we had to really kind of give a quick analysis of, the amount of agglomerations, the size of them, that type of thing. So that's how we did it. It was purely through the digitization of this particular microscope we're using at the University of Maine.
Okay. How did you select the graphene manufacturers for the study?
Sorry, I was on mute there. So the Graphene Council has over 40 graphene producing companies that are members of the Graphene Council. All of the members were made aware of this study, and they were able to voluntarily decide if they wanted to submit samples for testing. And in some cases, we had manufacturers that would submit more than one sample. And that's why we ended up with this broad array of a graphene oxide, a reduced graphene oxide, functionalized, non-functionalized, and graphene nanoplatelet materials, which is fantastic for the study because we could see that full spectrum of these different types of materials. The other thing I would say, and Jason mentioned this, and I think Paul as well, is that we did not optimize, right? We just wanted to take head-to-head, take the material, do a standardized approach in terms of dispersing and then testing the test coupons and see what the results are, right? Without trying to tweak them or trying to optimize for best results.
Right.
Now, what that means is that some of the materials that even may on the results that we had displayed in this study that didn't perform as well as one might have hoped, it doesn't mean that they could never perform well if they weren't optimized. So a lot of this comes down to really, each of you who's working with creating a composites part, you're going to have your own special kind of formulations, maybe some of your additives. You're going to have your special engineering objectives, because certain flex, impact, resistance, strength, all these parameters that you want to influence. What this really does, if you think about it this way, you have this palette of graphene materials that can be applied at very low load factors and can tweak these engineering outputs in a variety of ways. So it gives you a lot of engineering options that you didn't have before. This is what's so interesting about it. So if you wanted to reduce flammability, but you want to increase strength at the same time, or whatever the combination is, or you want to use this with a carbon fiber or with a basalt fiber or with a glass fiber, you have a way of mixing and matching and tuning these graphene nanoparticles in different ways, because they can be changed with functionalization. They can be changed on carbon layer count, 1 layer, 3 layer, 5 layer, 7 layer. They can be changed in lateral flake size. You have all these ways then of tuning them, which really opens up opportunities to take your composite up a step change performance level with a really small additive. And because you're using such a small fraction, even at a nominally high price per kilo, right? Say $200 a kilo, or $100 a pound, which may or may not sound expensive. The actual impact on the finished part becomes quite minimal, especially considering how much performance you get out of it. So I think we should not lose that bigger picture, is that this is just opening up a palette of opportunities for you as engineers.
Terrence raises a couple of really good points. I hope you don't mind my interjecting here, Terrence. What I notice about this is that just because a graphene didn't perform as expected or hoped in this particular study, doesn't mean if we didn't do a different study, a different matrix, different resin, it wouldn't perform very well. Each of these samples that we looked at was unique, and each of them was different. And if you change the test conditions or the test parameters a bit, you could be looking at somewhat different results. We even saw that if you change the loading, it also changed the results. So maybe what was the ideal loading for some samples was not necessarily the ideal loading for others. These are some of the variables that can affect it. And the other thing is, you can really get it's a very significant amount of performance, as he's noted, at very low loadings from the use of the graphene, so that you actually get a bigger bang for the buck from using graphene for your end molded part. Than you do just from using, in theory, than just using the neat resin by itself. That's a point I kind of wanted to throw in there.
Yeah, absolutely. Next question here. Is there a health or environmental risk at end of life when disposing composite structures with graphene, similar to concerns with carbon nanotubes?
I'll jump in on that one just because we've kind of looked at that and defer to my colleagues here if they have something to add. So the Graphene Council is actually involved directly with EPA on registration of graphene under TSCA. And in fact, next Monday, we have a webinar on this topic where we have 2 representatives directly from EPA to discuss the registration around graphene as a material. Now, for the dispersing or for the disposal of the material at end of life, the studies that we have seen, and there was just another recent one out, was that once graphene is incorporated into these parts, especially as a solid, it is virtually impossible unless you dissolve the matrix to liberate the individual graphene particles. In other words, if you took a composite material formed into a solid part and then sanded it, you are not going to liberate individual graphene flakes out of that that plastic. So
It's too small.
And then on the recycling side, because graphene improves the strength performance. So if you had thermoplastics, for example, that you wanted to recycle, we actually have cases of using graphene to improve the recyclability of those materials, to improve their performance. So it actually enhances the recovery of those materials. And with that, I'll stop there.
Yeah.
Okay, excellent.
Yeah, Pete. The only thing I'll add to that is that graphene is very, very small, and just by sanding it, you aren't going to expose it because your pores of your sands are much too large.
Okay, no, that's a great point. Does the addition of graphene affect resin infusion ability?
I'll jump in. You guys add to whatever I'm going to say here. So 2 things.
Jason, what do you think?
It does affect viscosity. So as long as you can, at this particular low loading at 0.1%, we believe we can keep the viscosity low enough that it's still infusible, right? Infusion is all driven by Darcy's law, and as long as the 3 main variables are controlled, you're going to be fine. So I believe we can keep the viscosity low enough.
From my standpoint, I don't think it'll have much of an effect.
Yeah. There's another factor that some people bring up, and that's filtering. Will the graphene be filtered out? Should not. At the size that these particles are at, there is enough porosity in any ply stack that it's able to filter through. If the resin gets through, the graphene will get through. There is no filtering effect because of the size of it.
Okay. Regarding graphene properties, can you explain the performance properties of graphene in regards to anti-corrosive properties, for example, in heavy-duty protective coatings?
I'll comment on that in 2 ways. So there's use of graphene for anti-corrosive properties because it's non-reactive. So if you think of the petrochemical complex where you're using pipes and you come into this corrosive material, graphene is used as a barrier for anti-corrosive properties. If you're thinking of rust and things like protecting metal, it's used in paints, again, for its anti-corrosive properties. And we have a lot of test results from saltwater tests and exposure tests over a long period of time that shows it's one of the reasons why graphene's used. And it's because of the tortuous path concept of you have platelet over platelet that performs a barrier. A pure sheet of graphene will not even allow a hydrogen atom to pass. Okay, it's impermeable. Now, when you're using platelets, obviously you do have spaces between the platelets, but it is quite often used for that. And then the other way that it's used for some of this high performance or corrosive environments or friction environments is it improves the wear. And so you have less degradation from wear if you've got a physical wear of a part, which is why it's used, for example, in the mining industry for polyurethane components that are high wear with friction with rock and stone and steel. So I hope that answers. I think that should answer that particular question.
All right, excellent. Within the study, how did you evaluate the resin wettability on the graphene or graphite interlayer spaces in the carbon materials?
How do we evaluate the interwettability?
resin wettability?
Rheometrically. We looked at when we started off with the raw powder, we took a measurement at various shear rates on the material as dispersed at various loadings, and then we changed the loadings, and then we dispersed it to varying degrees, and we measured the change.
Okay. How many samples were made with the 0.1% loading, and did you see differences from batch to batch variation?
So
I'll tell you, yeah, there were, we only worked with this very small sample, like 50 grams of each sample. And so we had to dilute that to concentrations in a master batch varying from say 1 to say 20% loading in order to achieve the rheological stability that we were after. And so, okay.
Yeah, let me just jump in. I think what they're steering towards is the number of samples, and we did at least 5 samples of everything: the 0.1% loading, the 0.5% loading, the base loading. We actually did more than that. But in our experience, statistically, you want at least 5 samples to know you have significance there. So everything we did 5 samples with, and that's what we ran with.
Okay. So you mentioned hydrogen vessels at one point here, but what type of graphene additive would you say would better act as a gas barrier for CFRP hydrogen vessels?
So this is just very generally speaking. If you're looking for barrier properties, then larger lateral flake size would typically be something that you'd want to have versus a smaller flake size. But at the end of the day, there's also a cost performance barrier here. So you'd want to match the right kind of material for the particular use. And this is also where perhaps a graphene oxide might work. And graphene oxide, which has a high oxygen content, can actually be put into a part and then reduction done in situ. So there's, again, I don't want to sound like, a typical consultant might sound to say, well, it depends on every answer. But you do have different, it's not like one type of graphene is the right answer for every one of these solutions. And you do have opportunities to play with some of the different properties of the individual particles. And then also there is a very wide price range of the graphene material itself. And so you might want to look at some of those economic trade-offs at the same time. And there's higher tolerances required. So if you have a pressure vessel that's going into outer space, for example, where you've got really wide temperature swings, then you might look for a particular type of material there as opposed to one that's used for fuel transportation on terra firma, right? So it really does depend on the operating environment and the host material and all these other factors.
Mm-hmm.
Let me jump in there and just speak kind of in general terms. We're talking about a lot of different applications and a lot of specialization. There's really kind of two different levels we're offering here. First is an off-the-shelf system that we've developed, right? Easy, blend in, you're going to get improvements. But then there's optimization, where we can lean on the Vibrance guys and their expertise, Paul and Santosh and the others, to say, okay, here's a customer that has this need, and we need to, whatever it is, pressure vessel, whatever it is, we need to optimize for this particular application. And then we can dive into it and really customize it utilizing Vibrance expertise. So you kind of have two different things here that we can work with you on both levels. So the key here is just reach out to us. Let's talk about what your needs are. If it's an off-the-shelf solution, great. If it's something where Vibrance needs to really get technically involved and bring in a lot of customization, then we can do that as well.
Jason, I think that's a great point that you add. In the Graphene Council, just to put this in perspective, we do not make graphene. We do not sell graphene. We don't get commissions on graphene. We have graphene companies as members. And then for your requirements, we can also help then identify the supply chain partner on the graphene production side, which works together with companies like Vibrance, like CompositesWorld. At the end of the day, because if you're going to scale this up, you need to make sure you've got good supply chain on the back end. And that's the part where we come in, is agnostically helping to connect the right graphene producers, or several of them, into your supply chain with experts like Vibrance and CompositesWorld for the delivery.
Okay, that's excellent. The next question is about comparing use of graphene or within an additive for epoxy, like you were doing in the study, or as part of the layup material itself, such as Kevlar. Is that something you can speak to? It says which way would have the bigger impact. You want to speak to that a little bit?
I'll jump ahead. So long story short, graphene has been prototyped, researched as a sizing material for fiber reinforcement, so that the graphene would actually be applied directly to the fiber as opposed to in the resin system. I think with the resin system, it's been promising because there's the control that you've witnessed through the study we've done, the ability to control the loading. But there is work at looking at putting graphene in to the fiber directly as a sizing agent. And the other way of looking at this perhaps is with prepreg as well, right? Is that you've got prepreg material as opposed to an infused resin system. But those are not as far along yet as what we're able to talk about here today.
What about, it mentions a number of processes here. Do you have experience with using graphene in processes like AFP or automatic fiber placement or additive manufacturing?
Yes, it's been used in additive manufacturing significantly. And then in the automated fiber placement, it depends on.
I think the answer to that is that's an open book.
Yeah.
Well, on the 3D printing, definitely.
Yeah.
Sure.
This question is, do you foresee a future where graphene enhanced extruded thermoplastic tape could compete with long fiber reinforced composites?
That's a big question. The answer is I wouldn't know. I know that we can improve, but can we improve enough to compete with that? I don't have the answer to that. I don't know if anyone else does here, but it will definitely improve. I just don't know how much.
Well, I'm not sure if this is exactly the same question, but sometimes when people hear about the amazing strength properties of graphene, sometimes people assume, oh, well, if we put graphene in the resin, we can eliminate the fiber reinforcement. And that is not the case, or I would never say that that's the case. I don't, I think that would be a rare case where you would eliminate the reinforcement completely in terms of thermoplastic composites or thermoset composites. So if that's the question, no, you're not going to replace the fiber reinforcement.
Right.
Question here specific to aerospace. It says one of the keys in aerospace is the desire to protect the purity of a qualified resin system, with fillers or particles seen as undesirable. This reluctance to add things to known resins tends to lead toward coatings on fibers or approval of prepreg systems that can be modeled. Do you see this as an issue for the master batch route to market?
For production, yes. Anything that's going to be flying that needs FAA approval, obviously we can't just throw this in and expect it to be okayed. It's something where we'd have to go through the process of getting an NCAMP database or an AMS database behind it, and then get approval behind all of that. That's an enormous process. So yes, we couldn't just throw this into one of the systems out there that are already in use in aerospace, but we can develop something and grow something and make it useful for that type of aerospace application.
Okay. We'll go with one more question here. Let's see. Does graphene help improve the interlaminar properties in a composite stack-up?
I am confident that it will. We did not test for interlaminar, but that will be one of the tests in the future that we move on to. It's just a matter of getting that study together and the funding for it. But for me, I'm confident we'll show improvement there. What improvement, I don't know, but it is a resin-driven property, and we know we're enhancing the resin properties here with this enhancement.
Okay, excellent. So we're at the top of the hour here, I guess. So we've come to the end of the webinar, I guess. We do have a couple of questions that we were not able to answer live. These will be saved and forwarded to our presenters here to be addressed later. Terrence, Jason, and Paul, thank you again for this presentation. I really appreciate it.
Thank you.
Thank you. Thanks everybody for listening. Hope this was educational and helpful to you. And I know I speak on behalf of all of us that we're here to answer questions, and if we can be of help in any way, please don't hesitate to reach out.
Great.
Thank you.
Yeah, thank you from CompositesWorld too to our attendees for joining us today. We appreciate you being here, and hope you'll join us again for the next CompositesWorld webinar.